Hello everyone. In this video we will find the electric field outside a charged solid cylinder. Okay. So in my previous video we went through the solution of the first part, or part A, which we consider the solid or the cylinder as a hollow cylinder, okay, as a shell. But here we're going to do the part B. So simply we have a solid cylinder charged with a total charge of Q. The cylinder has a radius R and length L, and we want to find electric field at this point here, which has a distance D from the left side or the right side of the cylinder. Okay, so let's see how we proceed. So we are simply doing part B here. Consider now a solid cylinder with the same dimensions as before, as we mentioned, and we have the same charge uniformly distributed through its volume. And there is a hint or suggestion or help from the question. Tell us, use the result of example 23.3, which I'm going to explain what it is, to find the electric field created at point, which is this point here. It's called point P. So this example actually is about electric field at a distance D from a disk, or a distance x or d from a disk that carry a total charge of Q. So let's assume we have a charge. So this is this example. We need to find the end result of this. So basically this equation need to be given to us in order to be able to solve or proceed in this in the example that we're going to try to solve. So let's say this is a disk, radius of R and total charge of Q, and we wanted to find electric field at a distance of, at a point here, a distance x or d. So the answer, actually we got it before, for the electric field at this point was equal to this expression. Again, we should not memorize this, but we should be able to know how to get to this. So as I said, in order to proceed, in order to proceed, we need to have this equation in front of us, or this expression in front of us. So let me explain. So this expression simply gives us the electric field at this point P, which is in this example, it's far from the cylinder by distance x. Now sigma here, we could write it as sigma is a surface charge density. We could write sigma as total charge of the disk divided by the area of a disk, which is pi r squared. Right. So the expression of the electric field for the disk will be something like this. Will be 2 pi k, okay, multiplied by q divided by pi r squared, and then we have the term inside the bracket. Okay. So maybe we don't need this pi, we don't need this pi here. Okay. So let's proceed now for our example. We have a solid cylinder. We need to find electric field at this point. So first thing, we need to divide the cylinder into many small pieces. Each piece represents a disk. So let me show one of those disks. It's a disk, and the disk has a thickness, let's call it dx. So this is dx. And again, for simplicity, I'm going to say the x-axis starts from point P and going to the left, just to make things easy. So this is my origin here. Okay. So what we do, we divide the cylinder into many small pieces. The first piece located at x is equal to d. The last piece located, the last disk located at location L plus d. And one arbitrary disk located at a distance which is x. So this is x. So as you see, when you proceed from the disk, from the first disk to the last disk, the position of the disk keeps changing with respect to point P. Okay? So for that disk, for this disk, let's use the equation that we have it in front of us. And we're going to do a little bit, some changes, okay? So the electric field that produced at this point from the yellow shaded disk is going to be to the right. If I assume the disk is positive, the electric field, I'm going to write it as dE, because that disk carry a small charge, we're going to call it dQ. So dE simply equal to, I'm going to write this equation as is, equal to 2K multiplied by Q divided by R square. But we're going to do some change in that Q. Just give me a second. Multiply by the term X divided by square root. I'm going to write as square root R square plus X square, and then I'm going to close the bracket. Okay. See, in this example, the disk was carried a total charge Q, but in our example, the charge on the disk is dQ. So I need to change this Q into dQ. Okay? Into dQ. Again, this is electric field for one disk, but we have million of these disks across the cylinder, so we need to do integration. Integration, simply you add all this electric field in a vector way, and then the final result will be the total electric field. So the left-hand side, easy, is going to be equal to E, right? E. But before we proceed, we need to do something for this dQ. We need to write this dQ in terms of density, volume charge density, because this is solid cylinder, so charge is distributed over its volume. So for the cylinder, the volume charge density is equal to total Q divided by the volume of the cylinder, which is pi r square multiplied by L. This is for the cylinder. For the small disk, I can write volume charge density as dQ divided by the volume of the disk. Think about the disk as a very short cylinder that has a volume of r squared multiplied by dx. Of course, this is the same, right? So it means this side is equal to that side. So if we equalize these two equations, we're going to get dq equal to dx divided by L multiplied by total Q. Okay? So we're going to substitute this into this equation. Okay, and then we're going to proceed. So what I'm going to do, any constant that I know constant, I mean any quantity that I know constant, I'm going to just put it outside of the integration. So as we said, the left-hand side of the equation simply is electric field. It's just d, integration of d is equal to E, equal to. So we have the factor of 2, we have k, we have r squared, and if I substitute dq by dxlq, I could actually move q outside and L outside. So I'm going to have the integration of a term 1. So we have, remember, we have dq, so we have dx. Okay, so this is going to be dx, and this term will be equal to x dx, and then we have a square root. X squared plus r squared, or r squared plus x squared, doesn't matter, right? This is x, and I'm going to close this. Now, again, from where to where we should put our limit of integration? Well, as we explained, the first piece of the disk was here, right? Which is located at distance of d, so it means we are x is equal to d. The last piece is located at the very end, which is at a distance with respect to this point d plus L. So I'm going to write down d plus L. Now this integral is a piece of cake. It's very easy, right? It's actually two integrals. The first piece is simply equal to x, and the second piece also is. So let me just do the integral, and we're going to put these two terms, terms at the end, okay? So this is going to be something like that. So the first piece is going to be equal to x integral d plus L plus or minus integral. The second piece I'm going to write it like this. So I'm going to say x squared plus r squared, and then minus 1 divided by 2. And then we have x, we have dx. Okay? As usual here, we have two terms. What's the derivation of these two terms? It's 2x dx, but we only have x2 dx. So I need to multiply by 2 and then divide by 2. Why I did that? Because the derivation of these two terms is 2x dx, right? So this integral is going to be simply is going to give us x squared plus r squared to the power of half, because minus half plus half is half, and then we divide by half. So it's going to be integration. Sorry, this integration should not be here, right? The first one, because we have already done integration. So it's going to be x d plus L minus, this is 2 divided by 2. Why this is 2? Because in the integral we divide by half, so it's going to be here 2 divided by 2. Then this is going to be something like this, x squared plus r squared, and then again we need to substitute d plus L. Okay, I'm not going to do the last step, you know how to. So this term simply is equal to d plus L minus d, so it will be L, and this term, the second one, instead of x, once you write d plus L, and then minus, and then the second time you're going to say d squared. Make sure you, when you do this, make sure you bring this term over here. And this is the final solution. Okay, so as a summary, what we did, because the question was a distribution of charge, I divided the disk into many small disks. For each disk, we have the equation before. Okay, we use that equation. The only thing that I changed it was actually the Q. I made it dq, and I used the idea of density to write dq in terms of the total Q, and I did the integration. Okay, I hope this video is useful. Thank you.